Dear students, welcome to the second unit of software engineering. In Unit 1, you were introduced to software, role of software, characteristics of software, need for software, and software engineering. In this unit, we will learn what is a software process. Further, we will discuss different software process models, their weaknesses, and their strengths. After completing this unit, you should be able to explain a software process, discuss software process models, illustrate activities involved in each process model, and compare advantages and disadvantages of each process. Let's start with the process. A process is a series of steps involving activities, constraints, and resources that produce an intended output. For example, we want to develop a software. The process for developing software would encompass the following activities, resources, and constraints. The activities are: communicate with the customer, identify the requirements, check the feasibility, analyze the requirements, make a design, develop the software according to design, test the developed software. If software is according to the customer specification and free of errors, then implement it, otherwise repeat all the steps described above. Constraints are the following. Requirements should be carefully identified. Feasibility should be checked for the suitability of project in terms of software and hardware requirements, cost, and time. Problem should be carefully analyzed. Design should be made keeping reusability in mind. Testing should be done carefully. Resources are people, software, hardware, equipment, time, and money. Software process. Building a software product is actually known as software process. Many software process models have been developed. We will look at a few of the more popular software process models in this unit. There are 4 fundamental activities which are common to all software processes. These are: number 1, software specification; number 2, software development; number 3, software validation; number 4, software evolution. Different software processes decompose these activities in different ways. The timings of the activities vary, so the result of each activity is different. Software process characteristics. Software processes are complex and involve a large number of activities. Like software, processes also have attributes which are useful when analyzing and comparing different process models. Some of the important characteristics of process models are understandability, visibility, supportability, acceptability, reliability, robustness, maintainability, and rapidity. Let's discuss what do these terms refer to. Understandability refers to the extent to which the process is defined. It refers to the ease to understand the process definition. Visibility refers to that either process activities are properly performed and progress of the process is visible or not. Supportability refers to that either the process is supported by case tools or not. Acceptability refers to that either the process is acceptable or usable by those involved in it or not. Reliability refers to that the product developed is free of errors. Robustness refers to the continuity of the process in spite of unexpected problems. Maintainability refers to the adaptation of changing organizational needs. Rapidity refers to the speed of development of a process according to the specification. Now we will discuss software process models. Let's understand the term software process model. A development strategy designed to solve an actual problem in an industry setting is known as software process model. This development strategy encompasses the process, methods, tools, and the generic phases. Let's start with the Waterfall Model. This model is also known as linear sequential model. It is known as waterfall because it has separate and distinct phases of specification and development. Once a phase is completed, you can't repeat it. The waterfall model encompasses the following activities: requirements analysis and definition, system and software design, implementation and unit testing, integration and system testing, operation and maintenance. Let's examine the advantages of Waterfall Model. The Waterfall Model is simple to implement and manage. It enforces a disciplined software development approach. The Waterfall Model has certain limitations as well. These are: mostly customers can't state the problem clearly at the beginning of the project, but as the project evolves, they feel certain changes in the system. Waterfall Model is unable to accommodate changes at later stages. A working version of the software will not be available until late in the project time span. This can lead to the development of software with a major mistake. Iteration cannot be accommodated easily. Deadlock can occur if any developer delays any steps in between. Method is not suitable for large projects. Modified Waterfall Model. One way to improve the model is to use prototyping approach, which is to define the customer requirements, design the project on paper, discuss with the customer if he is satisfied with the final layout of the project, then develop it according to Waterfall Model. The prototyping model is generally useful when the customer is not sure about the detailed input or outputs and requirements. Ideally, the prototype serves as a mechanism for identifying software requirements. Generally, the customer and the developer define the overall objectives for the software, identifying whatever requirements are known and outline areas where further definition is necessary. A quick design is then built, which leads to the construction of a prototype. The quick design focuses on a representation of those aspects of the software that will be visible to the user, for example, input approaches and output formats. The prototype is evaluated by the user and used to refine requirements for the software to be developed. Iteration occurs as the prototype is tuned to satisfy the needs of the customer. There are basically two approaches to prototyping: throwaway or closed-ended, evolutionary or open-ended. In throwaway approach, the prototype is developed from an outline system specification. It is then delivered for experimentation and modified until the model is entered. A specification is then derived from the prototype and the system is re-implemented in a final production version. Components from the prototype may be reused in the production quality system. In evolutionary approach, development starts with those requirements which are best understood. First of all, an abstract specification of the system is developed from these specifications, and then a prototype system is built. Using this prototype system, development is completed. Then the system is checked for performance. If it adequately meets user requirements, then it is delivered to the customer. Otherwise, a new prototype is developed and the whole cycle is repeated until the development of proper system. If we compare the two approaches, we find that the objective of evolutionary prototyping is to deliver a working system to end users, whereas throwaway prototyping only validates or derives the system requirements. Now let's discuss advantages of prototyping model. Prototyping models are appropriate for small or medium-sized interactive systems, for parts of large systems, and for short lifetime systems. Shortcomings of this process are that there is a lack of process visibility. The developer often makes implementation compromises in order to get a prototype working quickly. An inappropriate operating system or programming language may be used simply to demonstrate capability. After a time, the developer may become familiar with these choices and forget all the reasons why they were inappropriate. The less than ideal choice has now become an integral part of the system. Special skills may be required, for example, learning 4GLs and case tools. Rapid application development is a high-speed adaptation of Waterfall Model in which rapid development is achieved by the component-based construction. If requirements are well understood, a fully functional system is developed within a very short time. The development may typically take 60 to 90 days. Phases of RAD model. The RAD model encompasses the following phases: business modeling, data modeling, process modeling, application generation, testing, and turnover. Let's discuss these phases in detail. Business modeling. Information flow between business functions is modeled to answer the following fundamental questions. What information is generated? Who generates it? Where does the information go? Who processes it? What is the functionality of the system? Data modeling. The information flow defined as part of the business modeling phase is refined into a set of data objects that are needed to support business. The characteristics of each object are identified and the relationships between these objects are defined. Process modeling. The data objects defined in the data modeling phase are transformed to achieve the information flow necessary to implement a business function. Processing descriptions are created for adding, modifying, deleting, or retrieving a data object. Application generation. Rather than creating software using conventional third-generation programming languages, The RAD process works to reuse existing program components. In all cases, automated tools are used to facilitate construction of the software. Testing and turnover. Since the RAD process emphasizes reuse, many of the program components have already been tested. This reduces overall testing time. If a business application can be modularized in a way that enables each major function to be completed in less than 3 months, it can use RAD model. Advantages of RAD model are that it provides high reusability and more productivity in less time. Shortcomings of this model are: if high performance is an issue and performance is to be achieved through tuning the interfaces to system components, the RAD approach may not work. RAD is not appropriate when technical risks are high. This occurs when a new application makes heavy use of new technology or when the new software requires a high degree of interoperability with existing computer programs. Evolutionary software process models. Process models that have been explicitly designed to accommodate a product that evolves over time. Evolutionary models are iterative. They are characterized in a manner that enables software engineers to develop increasingly more complete versions of the software. There are 3 models to be discussed in it. Number 1, the incremental model. Number 2, the spiral model. Number 3, the concurrent development model. Let's discuss these models in detail. We start from the incremental model. This model combines elements of the linear sequential model with the iterative philosophy of prototyping. Each linear sequence produces a deliverable increment of the software. For example, you develop a website and provide only a few important features in it, like admission form, mail to, an introduction to university, and in the next version, you add few other important features in it, like link to virtual library for students, etc. Then an incremental version is produced. When an incremental model is used, the first increment is often a core product. Basic requirements are fulfilled at this stage, but many supplementary features remain undelivered. The core product is delivered to the customer. Customer uses it and tells which additional features are required to be added in it so as to develop a complete product. If we compare incremental process model with prototyping, we find that incremental model delivers an operational product in each version, whereas prototyping does not. Advantages of the incremental model. Incremental development is particularly useful when staffing is unavailable for a complete implementation by the business deadline that has been established for the project. Early increments can be implemented with fewer people. If the core product is well received, then additional staff can be added to implement the next increment. Increments can be planned to manage technical risks. For example, a major system might require the availability of new hardware that is under development and whose delivery date is uncertain. It might be possible to plan early increments in a way that avoids the use of this hardware, thereby enabling partial functionality to be delivered to end users without inordinate delay. Next one is the spiral model. The spiral model was originally proposed by Boehm. It is an evolutionary software process model that combines the iterative nature of prototyping with the controlled and systematic aspects of the linear sequential model. It provides the potential for rapid development of incremental versions of the software. Using the spiral model, software is developed in a series of incremental releases. During early iterations, the increasingly more complete versions of the system are produced. It is called spiral model because at the end of each phase, a complete version of the product is produced, which is further improved at the next phase, like a spiral enhances at each phase. A spiral model is divided into a number of framework activities, also called task regions. Typically, there are between 3 to 6 task regions. Figure shown depicts a spiral model that contains 6 task regions: customer communication, planning, risk analysis, engineering, construction and release, customer evaluation. As this evolutionary process begins, the software engineering team moves around the spiral in a clockwise direction, beginning at the center. The first circuit pass around the spiral might be used to develop a prototype and then progressively more sophisticated versions of the software. Each pass through the planning region results in adjustments to project plan. Cost and schedule are adjusted based on feedback derived from customer evaluation. In addition, the project manager adjusts the planned number of iterations required to complete the software. Unlike classical process models that end when software is delivered, the spiral model can be adapted to apply throughout the life of the computer's software. The new product will evolve through a number of iterations around the spiral. The spiral model uses prototyping as a risk reduction mechanism, but more importantly, enables the developer to apply the prototyping approach at any stage in the evolution of the product. It maintains the systematic stepwise approach suggested by the classic life cycle, but incorporates it into an iterative framework that more realistically reflects the real world. Advantages of spiral model are that: number 1, the developer and customer. Next one is the spiral model. The spiral model was originally proposed by Boehm. It is an evolutionary software process model that combines the iterative nature of prototyping with the controlled and systematic aspects of the linear sequential model. It provides the potential for rapid development of incremental versions of the software. Using the spiral model, software is developed in a series of incremental releases. During early iterations, the increasingly more complete versions of the system are produced. We discuss the concurrent development model. It is also called concurrent engineering. The concurrent process model can be represented schematically as a series of major technical activities and tasks. All activities exist concurrently but reside in different states. For example, early in a project, the customer communication activity has completed its first iteration and exists in the awaiting changes state. The analysis activity, which existed in the none state while initial customer communication was completed, now makes a transition into the under development state. If, however, the customer indicates that changes in requirements must be made, the analysis activity moves from the under development state into the awaiting changes state. Each activity has a state and exists simultaneously with other activities. Events from activities can trigger changes of state in other activities. The concurrent process model defines a series of events that will trigger transition from state to state for each of the software engineering activities. For example, during early stages of design, an inconsistency in the analysis model is uncovered. This generates the event analysis correction, which will trigger the analysis activity from the done state into the awaiting changes state. The concurrent process model is often used for the development of client-server applications. A client-server system is composed of a set of functions performed by the client and the server. When applied to client-server, the concurrent process model defines activities in two dimensions: system dimension and component dimension. System-level issues are addressed using three activities. Number 1, design. Number 2, assembly. And number 3, use. The component dimension is addressed with two activities: design and realization. Concurrency is achieved in two ways. Number 1, system and component activities occur simultaneously and can be modeled using the state-oriented approach. Number 2, a typical client-server application is implemented with many components, each of which can be designed and realized concurrently. In reality, the concurrent process model is applicable to all types of software development and provides an accurate picture of the current state of a project.